Hello, good afternoon, everyone. I'm Bilal Hadwi. I'm a computational scientist at the KAUST Supercomputing Core Lab. And it's my pleasure to host the seminar on overview of HPC numerical libraries and the success stories. And I'm honored to be joined by two great people, they are great developers of numerical libraries. So Hatem Al-Tayef, so he's a principal scientist at the Extreme Computing Research Center. And we have also Stefano Zampini. So he is a research scientist and PETC developer. So you will see, so here is the agenda of today. So I will try for the next half an hour, we'll give you kind of general introduction on the HPC numerical libraries. Then Hatem will give you some overview on the HPC dense linear algebra libraries, so from Plasma, Chameleon to Hikma. And then Stefano Zampini will introduce us a PETC and some success stories using OpenFOAM and SSDC. So the goal of this seminar is just to bring you awareness of your optimized numerical libraries on KAUST HPC resources, and you can apply it from your workstation and in any systems. And so the idea is to learn about the state-of-the-art numerical packages and to demonstrate how it is you can integrate it to your real application in astrophysics, in climate modeling, in CFD, and so on. And so the goal is to leverage it to get better performance. Okay, so I know this is kind of a preview overview. Hopefully we can follow up with some question, and later on, if needed, we can do much more detailed, let's say tutorial on these packages. So why you need HPC? So because you would like to get things faster. It's like when you have your car or internet when you feel it's slow and so on. And so sometimes you need to identify why it is slow, why my connection is slow, or why my car is not slow, is slow. So you need to check the and identify. And so this is we live in a time where time is money, and so you need to do to be productive. So you need to produce science. So your budget is kind of limited for your research, and also some of the resources are kind of limited and expensive. So you are lucky here at KAUST or in other center where you can have easily access to free resources. Also, most of you you would like to do more science to get the run code to get the code run faster, to perform more time step and higher resolution. Okay, and so solving problem is harder and longer. So, and when you look at the HPC application, most of them are solving linear algebra problem, and sometimes this problem can take from 5 to 90% of the total time of the application. And don't say, okay, this is only the old traditional, but also today it's the new, I would say emerging application. If we check the deep learning, when you see they are heavily depending on matrix multiplication, and even if it is small, but it is also a linear algebra operation. Also, when you see so there is a need of compute intensive kernel for HPC. So that's why you have numerical libraries. So you can use it for different a system of equation, for direct, iterative, multigrid solver, for sparse and dense systems, for eigenvalues and problems, especially people who like doing SVDs, least square element, or you need you are doing some signal processing, you do FFTs. So or you are trying to do a random number generator. Do you need to program all of this? No, don't waste your time. There are some people who dedicated that time, and so on. So you have more things to do, and so you need to be productive. So there are some people who did, I would say for you, most of the job. So for you, it will be just an integration. Okay, so it will be easy. I know sometimes when you see, oh, okay, it's too complicated, why I need to to optimize it. But there are people who dedicated their research. And this is, for example, what you will see by Hatem and by Stefano, who did the job for you. So for you, it's all that are here, the team can help you to integrate it and to get faster results. I give you an example. Okay, oh, I need to do matrix multiplication. Easy. Okay, I do a three-way loop. Okay, why I should bother? Why I should? But when you do small this, how it is running. So if you do this matrix multiplication is a 2 in a 3 cube floating point operation because you have 3 nested loop. So you have and y2 because you have 1 multiply and 1 add. So basically, if you have a small program size of n of size of 100, so this operation should take you probably 1 milliseconds. Or if you are running at using like one matrix size of 1,000, it should take 1 second, but in reality, no. So for 1,000, it should take you around like 6 seconds because the way like the pipelining is not, or the cache effect. While, so if you are using optimized vendor library, it will be only 2 microseconds. So you see the difference from 6 seconds to 2 microseconds on Haswell. So as I said, don't reinvent the wheel. So this is kind of the motto. So we are here because how you will take advantage of the new CPUs. It can be like on Intel, ARM, AMD, NVIDIA, and within the different network, it will be like a nightmare. So that's why, like as I said earlier, you have people who are expert, dedicated their research on optimizing this. So it will provide you what? Portability, modularity, and you will be more productive in like for maintenance and performance. Okay. So what does it mean, numerical libraries? So if you look at to the definition, so in CS, or if you look at the Wikipedia, so it's a collection of non-volatile resources used by computer programs, often to develop software. And so this may include like configuration data, documentation, and message template written. So basically this is that. And so basically, numerical library is a collection of function, routines, or class that can be implemented numerically. And so basically, usually this is our functional routines that you can call within any of your code. I don't say, oh, this is only for the old-fashioned way, it's only for C and old Fortran and so. No, we see it even for Python. Okay, and indirectly also, it's used by many applications like MATLAB, R, and so on. Which one to choose? So sometimes you say, okay, I heard like BLAS, LAPACK, ScalaPack, Plasma, DPlasma, OpenBLAS, Bliss, cuBLAS, Magma, whoa, I'm lost. Which one? Okay. We are allocated to have like so many things, but you have to know and choose wisely which one, because otherwise you will not achieve. And I like this picture. So, okay, you have like many ladders, but if you don't use it correctly, you will see like you will not achieve what you want to go. For example, getting the performance in our case, or to go and jump for his case, for the guy. So there are well-known packages. So we have in linear algebra, we have the BLAS, LAPACK, as I said, PETSI, we'll see later on, Hyper and Trilenus. So if you are doing like some signal processing, FFTW, if you would like to do like numerical integration, GSL, and you have also Spring, SPRNG for the random number generators. How I can use them? They are available. So you just do module minus S, and you will get the list of the packages. And this is like probably like I need like to remind you, like these packages, they have a very extensive documentation. I know like sometimes we're in a hurry, okay, we don't want to, but these packages, they all have a great documentation. They have a great example. So sometimes you just need to look to go, and sometimes you don't need like to look to their Bible, like of documentation of 1,000 pages. So you can go to the web page and you can just look at the routine that you need to use. On Shaheen, it's very easy. You just load any module and you compile. You don't need to change. And while in some packages, let's say on ABEX or on your workstation, either you install it your own or you have it, but you have to include the path and the flags. Okay? And also, don't forget to check and test. This is very important. We'll see later on. So now I will go to overview what are the BLAS and so on. So basically the BLAS is a basic linear, it means like a basic linear algebra subprogram. So basically they are composed in three levels. Sorry. Level 1 is for the scalar operation for vector. So you see this operation. So you have like X and Y is two vector, and then you would like to add with the, and then you, the operation is saved into Y. The level 2 are matrix vector operation. So, and this is a form here. And then the level 3 of what we call like +3, there are like when you try to do matrix multiplication. Okay, so easy. So I repeat. So you have kind of three BLASes: level 1 for the simple operation of vector, level 2, level 2. So basically here, the BLAS, it summarizes like many of operations that you would like with a vector, with scalar, or with matrix multiplication. And for the BLAS, you have to learn like the naming convention. So usually all the name of the routines are composed of like 5 letters. The first one, P, is the definition of the what kind of precision. So P can be S for single precision, D for double precision, C for single complex, and Z for double complex. Then you have MN. So what kind of matrix? It can be a general, so a general, or it can be band, okay? Symmetric, and so on. You have like different types. So you can even optimize into kind of storage. And then the last two, the like letter are in terms of common operation. So the dot is for scalar product, MV for matrix vector, SV is for matrix vector solve, MM is for matrix product, and SM is for matrix solve. So to try to do the inverse. So basically, so if I'm looking for a general double precision or single precision matrix multiply, so the name of the routine that I'm looking for is SGEMM. Okay, so now like if we have to learn something, is the name of the routine is easy to decode. So it's not a hieroglyph, don't worry, it's very easy. So you just need to remember like what each letter means. Okay, so DGEMM, it stands for double precision. Okay, and G is for general, and for MM matrix multiply. Okay, so here are like different, I'm giving you here a list of different BLAS. So you see like if you would like to do just a copy of a vector, you multiply by a scalar, if you would like to copy, and there is the name of the routine. Okay, you would like to compute like the norm and so on, so everything is already done for you. So you don't need to program this function. Some people did it and they did it in an optimal way. So this is a big difference. Okay, the same thing for the BLAS2. So we have a lot of bench of this. So don't worry, as I said earlier, all the slides will be available, and also the recording. And then the BLAS3. So as I said, like here you see, this is like for the SGEMM, for example, DGEMM. So you have to have like some parameters. So for example, the size, the scalar, the matrix size, the second matrix size, and then what is the output. Okay. So here is like the example of matrix multiplication application. So you have like so the trans A or trans B. So if you would like to have a transpose matrix or not, and you see like the size of the matrix A, so it's M by K, and then you multiply by the B matrix, so by K by N, and so the solution C. So when you multiply A by B, so it will be the size of M and N. Okay. And basically you just follow. So for you, it will be just a call to this routine and to with the right parameter that you need to call. Okay. Here is a very easy example when you see it, for example, for SGEMM. So you see here, like I'm just trying to do like random two matrices. Okay. And then when I call and I put the type, so that you remember when we say we need to check not only the that is working, but also the performance. Okay. And then here I put the size MN, K, and the alpha parameter. Here I think I put it to 1, if I recall correctly. Or here I just did another example. Okay, and you can have here like I like putting like the sources, so you can see here a lot of great examples. The same thing. So we went to from BLAS. Now we go for LAPACK. So it's linear algebra. So it's a higher level. So basically, like now we just saw routines like to do just the matrix operation, adding, multiplying, and so on. But you need like to solve now the system. You need to do like list work solution. You need to do like eigenvalues. Shall you do like the whole, or you would like to do a QR decomposition or SVD? Okay, they all depend on BLAS. So basically, inside of linear algebra, they are going to call the BLAS. Okay, and then you have the same nomenclature, like the same convention. So X, Y, Y, Z, Z. So it's like for the data type, the first letter, the matrix type, okay, and what you are trying to solve. So if it is a linear system, factorization, or eigenvalues, okay. And here I give the exhaustive list. So what you can do, for example, the people who are doing Cholesky, I know like many of you. So here you are looking for ways of the Chol or QR. Where is it? So yeah, there is like exhaustive, or you are trying to do like eigenvalues. The Q, yes, here are the, like for if you are like to do like the orthogonal piece for the Cholesky, like the orthogonal factorization. So this is what is needed for the Cholesky. Okay. Then okay, so we learn about LAPACK, BLAS, and so on. So you can just download the reference one. But however, this one they are not tuned. So they are just helping to take advantage of the blocks. However, like there are people like MKL. So some people, they did the auto tuning like Atlas or go to BLAS, but there are people who dedicated that time and they optimize it on the CPU or on GPUs. So for example, here you have Cray. So on Shaheen, you will need to use a libFCI. You have the Intel, so you use MKL. For IBM, it will be ESOL. And if you would like to go like for LAPACK, it will be PSL. So AMD, it used to be called like ACML. So now it's called AOCL. It's so this is new. And so by just linking and compiling with this library, so your code will not change. So just like if you call the BLAS, you can get a speed up of more than 10. Okay. So on Shaheen, by the default, you will have the Cray website. And if you're using the Cray compiler, so it will be already multi-threaded and so on. So you don't need to change. While if you're using the GNU compiler or Intel, don't forget to use the right flag. Okay. Well, here I think, oh yeah, here I need to update it. So it's -Q OpenMP for Intel. Okay. My advice when you use MKL, please check this advisory link, and it will give you all the details, all the link, so you're sure like how to compile it efficiently. Okay. Also a trick. So to get the timing of this function, so you can use the Cray website and you can add these two environment variables. So the Cray BLAS profiling and Cray BLAS profiling verbosity. So for example, by putting like 2, you could, like here I wrote a code. I put the export profiling verbosity 2, and I put the S1 minus no multi-thread. So because on Shaheen the hyperthreading is enabled, and here I'm just running a DGEMM for 1000, and I got the kind of profiling. And here by just like doing this export, I got an output of that saying, yes, you are doing a DGEMM of size 1000, and it took 0.002 seconds, so 2.8 milliseconds. And you see the performance is 700 gigaflops, which is great. Okay, we'll see it later on. Okay, yes, when we talk about performance, this is very important. Okay, so you expect, is it running fast or is it doing fine? So don't assume that what you wrote is going perfectly in the beginning. So check, always check. Okay, so like especially like for the BLAS tree, so it's quite intensive operation, and this is in order like a BLAS. So you see like this is kind of arithmetic intensity. So you need to check, like you try to be as close to the peak or very close to the order of your flow. So today, like the nodes now on Shaheen, IBEX or any, so they are in order of teraflop flops. So for example, Intel has one node, so it's close to 1.1 teraflop. Okay. So I did my first run on Shaheen, for example, and I did srun minus hint, minus n1 dgem and 1000, and I got only 46 gigaflop. Whoa, what's going on here? And when I look at it, 46 is very close to like only like one core is going. Okay, so the idea is, oh, let me do an export OMP num thread equal 32, and then I got a warning. So can someone tell me, yeah, I should have like hide the message output, and I got only 0.98 gigaflop. What's going on? Because, and you see the warning here on Shaheen, you have oversubscribed, because what it means, you are running on one core basically, and all the 32 threads or OpenMP are trying to run. So basically this is not right. Because why? If you recall what I said earlier, they are like libsci is already multi-threaded. Okay, so you don't need it to run. So you have to set up OMP num thread equal to 1, and then to run it. And then you specify if you would like to use all the threads. So basically POSIX minus C32, and you see 700. Yes, we got it. So you see the difference. So even you compile it, but you don't use appropriately like the threads, you may get, like you see, look at how many, like over like 700 times like slower. Okay, so be careful. Don't assume even you compile that is running well. Okay. Also, like for numerical libraries, there is a trick. Know what it's very important to know what you are doing, because sometimes you are not compiling correctly. And so use the minus L and comma minus Y dgem, for example, underscore, and you will know which library you are using. For example, here FTN, and here by default. So it will tell me like you are using the Cray libsci. And what I did, like to use the Intel library, so I need to unload the Cray libsci, and I put the whole line, So to make sure that I have indeed the Intel compiler. So you see, by just these two lines, I know like now I'm using the Intel compiler. So check with this function or any other function, you can do it for all the BLAS. So you can check which one your code is using. Okay. I will not go into the details, but just to tell you like the evolution and just try to be up to date. So numerical libraries, like people have worked on it like for more than 40 years ago. It started like in the 70s. If you know Jack Dongara, he's one of the father of all these libraries. So then it was involved like into like a Fortran, and then it went to LAPACK for the BLAS 1, then the BLAS 2, BLAS 3. Then they developed like LAPACK, as I shared with you, and ScalaPack. So basically everything is. And then in the late like 10 years ago, they started the initiative with Magma and Plasma. And so this is like to take advantage of the accelerator or the multi-core as of today we know. Like we're not running like only on one core now. And then now, like recently, if you look at the effort, it's called like Slate. So the people who are working on it are trying to not only to use efficiently for you, almost like transparently, the best performance of the today's and future machines, but also how to get the performance correct. And portability is very great. And here I would say like you are lucky that we have like two developers that who used to work on that. So two like myself and Hatem, the next speaker. And I know like several are like also worked on that, like mainly like from ECRC. If I recall, like we have at least like 4 or 5 alumni working at ICL. So this is great. So KAUST people are doing great in that. Okay. Okay, then you will tell me, okay, Bilal, you just show an example on Fortran C. We're coding now in Python. Yes, you can. And here I give you like some hints. So when you do the Python, it's the same philosophy. Try to see that there are packages. So try to use them. So there is NumPy. If your code, you are trying to do some matrix multiplication and you are not using NumPy, your code will be very slow. So on Shaheen, it's already available. You just do module avail minus capital S Python, and you will see the different. And when you try to check the Python, use this the np show config option. So you will see if your Python is calling the right libraries. Okay. And here I give you some hints like why it shows like also great performance. So why when you are not doing it correctly. So this is a very nice tutorial also. Here is a basic example. So you see, like to do like matrix multiplication, I just need like to do np dot dot. So it's AEB. And underneath, there is a LAPACK call. Okay, I will show you here. So here I loaded, for example, on Shaheen, module load Python 3.8.0. And this is our own installation that the KSL team, and probably you know him like our Python guru, Samuel Cortas. And you see here, it has been, the BLAS MKL has been done with Intel MKL. You see that here. For the BLAS optimized, so you see perfectly here. LAPACK with MKL, this is perfect, okay? So we are doing great. Oh, then you tell me, what about Cray-Python? Okay, yes, they did the same thing, but they have like also more advanced. So they have BLAS MKL. Oh, why? Why we don't have it? Because no, they have their own optimized. So you see, the MKL, yes, they don't have because it's Cray-Lipsci. So, and they are using like, it's based on OpenBLAS, but you see the optimized one, BLAS opt from the Cray-Lipsci. Also for the people who are going to run on AMD, check that. It's Bliss info because I run it on Shaheen. Of course, we don't have not available, but if I run it, for example, in one of the recent nodes of IBEX, I should try to get like at least Bliss, because Bliss, even though like in Arabic it means something else, it's heavily performing well on AMD. So Bliss in Arabic means also evil. But however, in terms of performance, if you're using AMD, this is based on all the performance will be get from the Bliss. Okay, so always check what you have. Okay, I will not go like my time is almost over. So there are several libraries, so please check them. Also, I know many of you are using like PETC, TPSL that have a lot of dependencies, Parametes, Hyper, Sanders, and Scotch. So check. If there is a library that you don't have or you don't know how to compile, please contact us. So you have our email here at help@hpc.kaust.edu.sa. Okay. Here I will just show like a brief example, like where I just have a code where I just compile it with the right libraries with different compiler, and I got over a speed up of 4. Okay, you see? So, and then if I compare with the default one. So this was like a work I did like 6-7 years ago, and this is still available. Like recently also I worked like with colleagues at KAUST, and by just changing the function, like he did like some loops, and we integrate LAPACK function and BLAS function. Overall, his application was like we got a speed up of over 11x. So just write the right, get the right library, and you should get the performance. Okay, so as a conclusion, I know like sometimes like old books like numerical recipes, they help you like to write code, but they are not optimized at all. Don't try to reinvent the wheel. Some people have done the work, and we'll see the talk of our next two guest speaker, Hatem and Stefano. What we have seen like briefly, like the environmental variables are very important, and the use can yield significant performance. Okay. Last but not least, try to check the performance. Okay, one optimization, and last but not least, read the manual. It's very important. I attend the tutorial workshop. That's why we are doing that. Okay. Thank you very much. Here we have like a couple of minutes for any questions.
Hello, can I have a question?
Yes.
Yeah, so basically, are you saying that if we just use Python, we can also make use of the Intel MKL library to do multi-threads and multi-core computing?
Yes, of course. And you see like here in the example here where I share. So this is where you need like to make sure like this is already optimized. So basically like if, for example, if you are on Shaheen or on Ibex, you can load this library. And here I showed you if you have, for example, the optimized one. So this means like you are going to take advantage of the threadings, multi-thread on the node. Okay. So you see here pthread. Pthread means like you are going to take advantage of the pthread. So for example, if you are a node on Python and you are a node of 32 or 40 cores, then you will know that it will optimize everything.
Okay, so yeah, the next question is where can I find the relevant information, for example, the manual and detailed implementation examples for this use of Intel MKL on Python, for example.
Okay. So in on Python is very transparent for you. So make sure that you are using, as I shared like earlier, you use the NumPy. Make sure that you have the NumPy.
Yeah.
Okay. And then for you, you just need to call like the function np dot, for example, for doing like matrix multiplication. Okay.
Okay.
You can have it if you call like if you check like a NumPy documentation. And here I gave you like some of the tips, but basically for Python you just need to call the NumPy libraries, and underneath it's transparent to you. It is going to call like all these BLAS and LAPACK function to you. Like for people who are doing MATLAB or R, so check the optimize. Don't do like a for loop and so on. So and if you have any question on that, we can help you in finding the right way to write the code.
Okay, great. That sounds easy. Yeah, thanks.
Okay.
Yeah.
Thank you very much. Okay. So now I will leave the floor to the second speaker. So we're right on time. So Hatem, so I will stop sharing.
Okay, thank you, Bilal. Let me see. Okay. Okay. All right. So thank you, Bilal, for organizing this seminar about overview on HPC numerical libraries. I'm extremely happy to be here and to share with you some of the things we've been doing in our center, running a new algorithm, trying to extract performance more and more on Shaheen and elsewhere. And we'll be also sharing some of our successful stories. A lot of works I'll be presenting with people at KAUST in our group. in our center, people from the supercomputing lab at KAUST and collaborators elsewhere. Vendors, these are the guys that keep funding us, giving us free hardware and giving us, remote access to emerging, or new architecture. And we are happy to have active collaboration with all of them. We all here actually today to see how we could juice as much as possible performance out of our Shaheen supercomputer. Okay, there are a lot of work at the moment in trying to procure Shaheen 3, and our people from our colleague from the supercomputing lab are handling that huge task for us. So what is really important is to understand, whether it's on Shaheen or another system, how you can really extract performance. When you look at some of the application being run on Shaheen, and actually this is also the case in many other supercomputers, you have many applications that consume lots of core hours. Those are the main, I would say, customer of supercomputing facilities. You have people doing material science, trying to understand the electronic structure of some material, people working on earth science field, trying to, for instance, the oil and gas industry, people doing climate and weather forecasting. We have many of those people at KAUST, and also astronomy. We don't have actually astronomer or astronomy discipline at KAUST. That's too bad, given the historical contribution of the region to the field. But at least we try to collaborate with some astronomers located internationally and try to speed up their performance. So in our center, just to giving you a bit more of the whole story here, in our center, we look at ourselves as an hourglass where we have many applications and we have many architectures. Okay, so how can we bridge those two worlds that looks like really disconnected, looks like swimming on two swim lanes? And the good thing is we try to make a bit our life easier, because we cannot be expert in chemistry and earth science and whatnot, and at the same time being close to the hardware from the vendor, NVIDIA vendor, Intel vendor, AMD, and whatnot. So we try to find a common infrastructure. We try to find a common denominator, and if as soon as we've done that, we could really improve that common denominator, try to extract performance, and then all of a sudden this translates into servicing or giving a huge performance boost to many applications on various architecture. Okay, so this is where we are located, at the waist of this hourglass, and time to time we try to be on Twitter and Facebook, on social media. Giving a talk in HPC and linear algebra without showing that graph is would be a bit awkward. I won't spend too much time. For those that are not really familiar with such a graph, we're looking at the top 500 list. This is a list ranking the 500 fastest supercomputers in running a given benchmark, so-called LAPACK benchmark. So the blue curve, so you have the years, the historical years, right, on the x-axis, and then the y, the performance recorded in running that benchmark. 3 curves. The blue curve is the system that just made it to the list, number 500. The orange curve is the number 1. And the green curve is, if you sum up all those 500 entries of the top 500 list, you get the performance. So we've been following this exponential growth as far as HPC, a supercomputer are concerned with the hardware. Thanks to the hardware technology scaling, we've seen a tremendous boost in performance over the last 3 decades. Okay, and all this is happening because the hardware really are exposing a huge amount of parallelism, and that benchmark in particular is able to take advantage of that parallelism. So now for any other application that are more, I would say, where more science is being done, it's really important to also follow a similar track where you want to expose parallelism and try to, have a huge occupancy on your hardware. And This is another graph showing a bit the microprocessor trend data, looking at how the hardware people have been working hard in doing revolution in that field by again putting lots of cores with lots of transistors in order to for application people to take advantage of those unprecedented level of parallelism. There are a lot of constraint, of course, physical constraint when you design those chips related to power dissipation, related to the frequency, the number of transistors, how many you could put on at a nanoscale, right? So there are a lot of technology scaling happening there. But the take-home message really from that slide is, is the time for the software people now, right? It's really the time for software people not only to recompile on a given new system and get performance by just recompiling. I mean, life sometimes is not as easier as this, although we wish that it is the case. But really to rethink, redesign the algorithm that that is the most time consuming in their application, and see how that algorithm could further extract performance on a given hardware. Okay, and this is sort of the cartoon showing the HPC recipe, right? This is a standard sort of recipe that could be applied in various applications, to again boost performance on those massively parallel hardware architecture that are coming, that are actually here today, and they are even coming in the next few years. So those are the few ingredients that I think are really important to make sure you deploy them, you use them into your application. Things like data motion reducing, synchronization reducing. You can't afford to run an application on a system with hundred thousands of threads and telling all those threads to synchronize, because you need to do some sort of reduction, for instance. This may occur. I mean, this may not be also an option to your application, but at least you should try. You should think on how perhaps you should redesign your actual algorithm to avoid such synchronization point that may really impede your parallel performance. Other ingredient like fine-grained parallelism, right? You need to split your huge computation into smaller computation that could run concurrently, that could run asynchronously, right? And that fine-grained parallelism is important again because it helps weakening some of the synchronization points you may have in your algorithm. And those are the things that I'll be discussing here. So this is a cartoon showing the algorithmic trends in numerical libraries, in high performance computing numerical libraries. So on the Y axis, you have the algorithm trend. On the X axis, the hardware trend. And there are many optimization, many new algorithm idea and innovation that happened along the last decade to again revisit the algorithm, revisit those linear algebra libraries that most of application rely on to extract performance. And while this was happening under the hood, and a lot of work have been done in a sort of kind of co-design way with the hardware people, performance boost has occurred in various applications, and I would describe some of them. And for some of them, even if you were to redesign the algorithm by matricizing further your algorithm, by expressing your model perhaps, or your optimization or your underlying problem that you're trying to solve in terms of matrices, you could get even higher performance improvement thanks to some fast hardware support in doing matrix multiplication that we've seen from various vendors. Okay, so those are really important insight to know about how the hardware vendors are moving forward, so that where to put your eggs as far as developing your algorithm. Where what are the trends you need to follow so that you can get a max benefit of what the vendors are doing. And this boils down to HECMA library. This is a library that we working on in our group, in our center, and we believe that library will help us solve many scientific problems at scale, problems that would not have been possible to solve before. And this requires lots of algorithm redesign, as I mentioned, and a lot of performance optimization, and also, teaming up with people outside of our own expertise. So, we look at it as really a multidisciplinary, project, and where a lot of people contribute. A quick look back I want to give here, just to echo a bit what Bilal has said in his first, talk. We've seen linear algebra libraries in the 70s relying on this level 1 BLAS, mostly memory-bound type of operation. And this was during vector operation back in the 70s. In the 80s, with the introduction of cache-friendly architecture, and we've seen the development of level 3 BLAS operation, where you could have or express your matrix in terms of matrix-matrix operation, express your operation in terms of matrix-matrix operation, with lots of data reuse that happen in cache, so that you can get performance improvement. In the 90s, we've seen we went from LAPACK for shared memory to ScalaPack for distributed memory, and this happened with the the trend of Beowulf cluster back in the 90s. In the 2000s, early 2000s, we've seen the development of Plasma and Magma library. Those libraries that basically split the matrix into small blocks, right? If you recall the fine-grained parallelism that I mentioned earlier as an ingredient for HPC recipe for exascale. So this is it. So what Plasma and Magma and even the newer library called Slate is doing is trying to split that big matrix that we've seen in LAPACK into two-dimensional blocks. And each of those blocks, an operation will occur on it. An operation will work on this data that is delimited by this tile. And what happened is you end up having a DAG, a directed acyclic graph, where the nodes correspond to tasks, okay? And the edges are data dependencies. All right, okay, so those are quick facts on LAPACK and ScalaPack. I'm moving quick. I want to spend just 1 minute here in this cartoon showing how this fork and join paradigm that is, I mean, still the main food for the main the main thing for LAPACK. But it has it's inherently problematic. It has lots of synchronization points, and again, I'm echoing here the synchronization reducing ingredient that I mentioned. Here, what happens is when I'm doing this matrix factorization in LAPACK using this block algorithm, I need to block some operation in what we call panel and then update my trailing submatrix. There is a huge synchronization point between those two, phases, and the parallelism really happened in the magenta, or I mean the pink or magenta area here, and in the green is mostly sequential. So what happened is you run sequentially most of your time here in the panel factorization. Then you fire your thread, and this is where you extract performance from your hardware. But then you move to the next step of your factorization, and you shut down all your thread that you started working on that trailing submatrix, because you entering a territory of the panel factorization that is mostly sequential. So this fork and join paradigm put lots of synchronization points that are problematic on today's architecture. So what we try to do then is we try to avoid those synchronization points. Before I move toward this, just a quick concept in understanding why level 3 BLAS. Bilal introduced level 1, 2, and 3, but I want to focus really why level 3 BLAS is important. This is where you have most of data reuse. This is where you will be able to extract performance. It does not mean necessarily that you will be faster, because if you have a code that is memory bound, mostly perhaps expressed in terms of level 1 BLAS, memory bound means that you are always waiting for the data to come. And once it comes, you don't do much operation on it. Okay, but it could be just the nature of your application, right? But what we try to, regardless, what we try to do is we try to make sure your data live as much as possible on registers, right? Because this is where you go fast, this is where you compute fast, and this is where actually computation happen. Okay. And just a quick example here, I'm showing you the performance of level 1, 2, and 3 BLAS in terms of how many operations per second you're able to do. And you can see if you do matrix multiplication, you get a huge performance boost compared to the other two level of BLAS that are mostly bound by the memory bandwidth. Okay, so I talked about LAPACK. I want to move to SCALAPACK. Those are the old algorithm, right? I'm just giving a quick or finalizing, the quick overview about LAPACK and SCALAPACK. So SCALAPACK take basically this block algorithm that I just showed from LAPACK and take it to distributed memory. So it adds the descriptor to basically describe how the matrix is being allocated or distributed on a cluster, on Shaheen, for instance, okay? And then it applies the same algorithm that LAPACK has, and it abstracts the fact that it's running on distributed memory with that descriptor, okay? So LAPACK and SCALAPACK are basically, state of the art, right? They've been there for more than 30 years. You'll find them in all supercomputers deployed today. They are used in many various applications. And there is an evolution, as I mentioned, right, from LINPACK to LAPACK to SCALAPACK. And what we've seen in the last decade is the development of new algorithm based on tile algorithm. And this is really an evolution, perhaps even a revolution, really moving to those tile algorithm. Okay, and the main idea of this plasma, right? So the main idea of plasma is, as I said, we split the matrix into blocks, right? I split the matrix into blocks, and then I try to redesign, or I need to redesign my algorithm so that it can run now on a data structure that has changed under the hood, right? So this may require really redesigning the algorithm. Once you do that, so you are able now to express your algorithm in terms of DAG, directed acyclic graph, and that DAG needs to be scheduled by a runtime system. The runtime system that comes with Plasma is called Quark. There are other runtime systems available out there, but the main idea, if I were to do, for instance, a least square solver before, I would just call LAPACK least square solver and I'm done. With Plasma, you also call Plasma least square solver and you are done, but under the hood, this is what happens. Your whole computation or QR factorization here and the corresponding solve will be broken down into pieces, into small tasks. And then you have a scheduler that come into the picture and a framework that would take that DAG and schedule it. As you can see here, the DAG is rather small. It's just a 5x5 matrix. The DAG here represents a 5x5 tile matrix. But it can go much bigger, much larger. And the way to look at this DAG is the width of the DAG tells you how much parallelism now you have in your application by going into fine-grained computation. The height of the DAG is the critical path, okay? Is basically how much steps are required for you, regardless of how many processes or resources you have available. That's the number of steps you will have to do to finish up your computation. But DAGs can be really complex. And there are many runtime systems, as I mentioned, that are available out there. OpenMP, for instance, has its own runtime system, but there are other runtime systems like StarPU, PowerSec, OMPSS, KAUST, for instance, and whatnot. There are so many that, in our case, okay. So what those runtime do, they basically have in their DNA this data flow programming. So it's like an assembly line. So it's like a producer-consumer type of relation. I'm doing a task once I'm done. That task has given produce some output that would be consumed by the next task, and so on and so forth. So you have to track and monitor the data dependencies, and those runtime are here for there. Standardization, this is really critical. There are so many runtimes available out there that we need to abstract them. And what we do here in our center, we use a library called L4SAN that abstract all those runtimes. So I write once a code, okay, a code that has some fine granularity and tasks with perhaps embedded into 4 nested loops. And I call L4SAN as an API to queue and run tasks. L4SAN under the hood would call the runtime of interest for you. But you just write once your code with L4SAN, and then L4SAN take care of making the right link, the right translation to the proper runtime that you are interested in. So you write once, and then you can run with Parsec, you can run with OpenMP, you can run with StarPU, and many of those runtime that are out there. And here's the performance, right? So moving from LAPACK to Plasma with tile algorithm, with dynamic runtime system, you get a performance boost, okay? And this is that performance boost that we are really after and trying to get even further, improved moving forward. One thing that I want to mention, we talked about LAPACK, ScalaPack, and Plasma libraries, right? We talked about runtimes. That is really the software layer that is really close to the hardware. That's the layer that gives you, again, performance. That's the BLAS, right? And some of the BLAS, it turns out that they are not really well optimized, implemented on some hardware. So we looked at them to try to improve them. And this is why we come up with our own KAUST BLAS, which look at some subset of BLAS, existing BLAS, but optimize them further for given hardware, okay? And one of the algorithms that we use for that is this recursive algorithm, okay? We use recursive algorithm to matricize further, to enrich further the BLAS with matrix multiplication, with level 3 BLAS routine that we know shine and extract most performance on any hardware, any vendor, okay? So by using this recursive algorithm, we are really able to get good performance. And this is part of a paper in Europar, and NVIDIA CUDA numerical library has also integrated our KAUST BLAS. And this is the performance, and this is pretty cool. I ran it just last week, actually. We took KBLAS, okay, and we ran it on 5 or actually 4 different hardware: NVIDIA, Intel, AMD, and NEC, okay? We use KBLAS, and we use this recursive formulation. Our recursive formulation does not code any new assembly or low-level BLAS routine. It actually called the vendor BLAS under the hood, okay? We're just reformulating the algorithm to make it more GEMM-oriented, to make it more, matrix multiplication-oriented. And what I'm showing here is matrix size and speed up. This is the speed up of KBLAS against BLIS, OpenBLAS, MKL, NEC scientific library, and cuBLAS, all on various architecture. So more than 1 is good. Less than 1, it means we are slower. And it turns out for at least 3 of the vendors, our routine today is still faster than their own routine. Okay, and this only with redesigning the algorithm. Okay, by matricizing further the algorithm. So this is the cool stuff, and we hope we got some discussion with NEC. Perhaps they will be integrating our KBLAS routine into their library. Another example, we also implement KAUST SVD, singular value decomposition. The singular value decomposition is the workhorse, algorithm in linear algebra. Okay, it's a very critical algorithm used in machine learning, used in PageRank, used in many applications. And this is the state of the art today. The left side are how Germany, US are doing business. In the middle, this is how Japanese are doing basically the singular value decomposition. We are doing it this way. Okay, we are actually doing it the way where we expose parallelism, because we know where the hardware is going. We know the trend of the hardware, and we know we need to break down our computation into small pieces to expose parallelism and get most of the underlying hardware. And by doing that, we're getting a huge performance speed up compared to ScalaPack from Cray scientific library, and we get up to more than 2x performance speed up. And this is just on CPU. This is actually run on Shaheen, on I guess perhaps 500 node or so node of Shaheen. And this gets us a cool, nice paper. And also, Cray Lab CI, when they've seen it, they decided to integrate that SVD solver into their own library. So this was really a good, one of the good successful story out of this algorithm. So if you recall some of the applications that ran on Shaheen, and actually in many other supercomputing centers, there were 4 of them, right? So material science, earth science, climate weather forecasting, and I also mentioned astronomy here. And you remember this waste of our hourglass where I said we try to identify the common denominator? This is the guy. His name is Cholesky. Okay, he gave his name to a nice factorization that we try to optimize like crazy on new hardware. And that Cholesky factorization is one of the most time-consuming operation on those 4 domain science that I mentioned. And you know how we do it in LAPACK and ScalaPack with those block algorithms that have many synchronization points and rely on this fork join programming model. We know about Plasma and Magma and Chameleon and Slate, all those libraries that take further, the parallelism out. by splitting your matrix into two dimension tiles. We're taking this we're taking it one step even further now. Okay, this was what we try to do here is we team up with domain scientists, and this requires, of course, lots of effort, but the reward is there because we also understand that we can, of course, build a Cholesky factorization that is completely agnostic to the application, or we could do one step further by doing a Cholesky factorization that is actually customized for the application, okay, for the application need that really is able to provide the right, optimization for the application. And what it turns out is, for some of those applications that I mentioned, the matrix itself is not dense. It's actually apparently dense matrix. It has a structure that is data sparse. There are some redundancy in the data. So that matrix, what it turns out to be is, if you generate it, it is dense, and you could do plasma and chameleon and slate and whatnot, to do your Cholesky factorization. But when we work with domain scientists, we figure out that those off-diagonal blocks of those covariance matrices, they are data sparse, so you could compress them, right? You could compress those blocks, those tiles, and retain only the most significant information. Okay, and by doing that, not only you are now able to save in terms of memory footprint, right, but also in terms of arithmetic complexity. You will do less number of operations now because you are working and deploying your Cholesky factorization on a data structure that is compressed. So there is a huge gain in two fronts. I require less memory, and I also do less number of operations. And all in all, the idea is that I go faster at the end, and not only faster, but also you are able to solve much, much larger problem that you would not be able to solve before, okay? And of course, I mean, accuracy, okay? You could tell, here when we approximate, when we do a compression of this tiny block here, we approximate up to an accuracy that is given to us by our domain scientists, our people that we collaborate with. Okay, and at the end, we make sure we reach that threshold for accuracy. And this is where HICMA comes to the picture. Okay, this is where HICMA comes as sort of renaissance in dense linear algebra, trying to take really this step further, where now I team up with domain scientists and look at their matrix and do much more than just brute force dense computation. And this is an example for spatial statistics that is used for climate weather forecasting. This is a matrix. Each of those numbers represent the most significant singular values that I need to retain to achieve that accuracy of 10 to minus 8. So my block here is 250 by 250. Out of those 250 singular values, I only keep here 27 because I only need 27, right, to get me to the right accuracy. And by doing that compression and associating now my new Cholesky that will operate on a compressed data layout with a runtime system, this is the type of graph that we are able to generate comparing HECMA against a dense Cholesky from Intel MKL, the vendor optimized BLAS, LAPACK, I'm sorry, on shared memory. We're looking at three type of curves, right? The graph shows time in Y, matrix size in X. So the lower, the better, right? So there are three groups of arrows. The red arrows are the speed up from hardware, but using the same algorithm, right? You have the same algorithm, but different hardware. This is the performance boost that you get with the red arrow. The green arrow is I have the same hardware, but the speed up comes from the algorithm, moving from dense to something that is compressed, right? Using this Steil-Lorentz compression. And that's the performance boost that you get from a software or an algorithm, improvement. Look at the difference, by the way, moving from, the improvement that you get from the hardware and the improvement that you get from the, algorithm. So, really the ball is on our side. I mean, the ball is on really the software development of our algorithm, hence the critical aspect of redesigning those algorithms. And when you put both, right, the blue arrow is when you have the improvement from both. You can reach more than 2 orders of magnitude performance improvement, right? So this is really, stunning number. We actually done also accelerated 3D acoustic wave scattering. This is in an application from in collaboration with the Hakan Bakshi group in computational electromagnetics. We run the HICMA LU, right? Before this was Cholesky here. Now this is LU factorization for non-symmetric matrix. We run it on various architecture: Intel Haswell, Skylake, Broadwell, Cascade Lake, AMD EPIC-ROM, and ARM, right? So you can see how our software is able to run on any, well, on most of vendor architecture, because we rely on BLAS, right? Because our application relies on BLAS, our algorithm relies on BLAS, we are portable, okay? Because there are no vendor out there that would put a new chip on the market without making sure the BLAS, works, properly on the hardware, right? This is how we get performance, sort of, portability, but also we are able to deploy our software on many architecture. And this was a work last year that gave us this best paper at ISC 20 conference. ExaGeostat, this is yet another work that we do with the computational statistics group at KAUST, led by Marc Janton and Ying-Sun. And this is the work also from done by Sameh Abdullah. So here what we do, we look at the covariance matrix that comes up from this climate weather application. And you could do it, as I said, the dense way, right? You would do business as usual, call LAPACK, ScalaPack, or Plasma, and you're good to go. What the people in the community have been doing, they were actually putting zeros there because they don't have enough memory to solve this huge matrix problem. So we came to the rescue, sort of, kind of, by saying, okay, no, we should not put zeros there, because there you actually zeroing out information that is really critical for your problem to work. So, we come up with this Taylor rank compression, and we retain most of the important information and carry on with the solver. The fourth approach that we propose is to use mixed precision, right? Those are covariance matrices. The farther you are from the main diagonal, the less accuracy you would need to perform your operation on. Okay, and those are the performance that I'm showing here, taking advantage of mixed precision, and that's something that applies in most of application, and I really wanted to emphasize that. It's an aspect that is rather emerging in the, emerging, perhaps not, but from an HPC point of view, emerging in the HPC community, during the last decade. And, one needs really to take into account that aspect and try to identify in your code algorithm application, room where you could do mixed precision. Why? Simply because in terms of performance, there is a huge gain. If you were to do this Cholesky factorization on 4,000 nodes of Shaheen in double precision, you will get 3 teraflop. If you do it in single precision, right, you will get more than 6 petaflop, not teraflop, 6 petaflop. And by doing it in mixed precision, because we can't afford go single precision all the way, we won't get the right accuracy. We go mixed precision, and we are able to get 5 petaflops. So there is a huge performance gain, because you would do everywhere double precision, but actually you would require only in some part of your matrix to do double precision. And elsewhere you could do single precision. And by consolidating those 2 precision in one operation, the Cholesky factorization, you get a huge performance boost. We went to HAWK. HAWK is an AMD EPIC node from Stuttgart, supercomputing center. I think is one of the top 10, if I'm not mistaken. Bilal maybe can correct me. I think is one of the top 10 in the top 500 list that appear last month. And the same thing apply, right? So they support single and double precision, and again, you can get a huge performance improvement by doing mixed precision. So this is really application dependent. It does not work across the board. You got to team up with domain scientists, identify where you could do this, and do it. And of course, you need to have a proper accuracy checking and making sure, whatever outcome is, you have ways and means to, check on your accuracy. It's good to go fast. It's less good to go fast and compute wrong. And those are systems that I showed, Shaheen and HAWK, that do 2 precision. But there are Summit. There are supercomputer out there like Summit that actually the hardware support 3 precision. You can go 3 precision, double precision, single precision, and even half precision. And look at the gain you could get on such hardware. Summit number, I think 2, number 2 supercomputer. If you were to do everything in double precision, you will get 3.5 petaflop, right? If your application is able to play with those 3 precision, you can, get a speed up of 3 there. So there is, again, a huge performance boost that you can get by identifying when and where you could apply mixed precision. Okay, I'm gonna perhaps skip this. This is just again showing a plot with mixed precision, but the cool thing is on the latest hardware, from NVIDIA, the A100, right? The A100 from NVIDIA gives you really this order of magnitude performance boost when you apply to it mixed precision and the right algorithm. So this is some of sort of the latest results we're able to generate on that system. We've seen some of those software solution we're providing in our center. We talked about KSVD, we talked about KBLAS, and those two ended up in Cray and NVIDIA numerical libraries. I'm going to look at and talk about quickly on KSVD and MOO. Those are the astronomy application, right? You remember I said, we are fans about astronomy. We even have, I think, an SCG group on astronomy at KAUST that get together time to time. We're also working, with astronomers from the 3 major worldwide ground-based astronomy, sites. The European Extremely Large Telescope, the Subaru Telescope from Japan, and the Very Large Telescope. So those are consortium. There are consortium behind those efforts, and they involve many countries. What are those ground-based telescopes are all about? In one sentence, they try to outsmart the atmospheric turbulence. The light that comes through the atmosphere gets distorted, and then when they look through the mirror and through the camera, the operator behind that camera, he's not seeing a clear light there. He's seeing distorted light, like what you can see here from the sun. And that's a huge problem because they are not able then to accurately identify exoplanet, for instance. Okay, so the way it works, again, they have those mirrors here that are deformable, and they can basically, they can compensate for the turbulence at real time. There is a whole simulation working in the background that tells those deformable mirror how to tilt in one way or another to compensate for those turbulence. Okay, and this is where we come into play. This is where we contribute and make sure that soft real-time simulation work and scale up as fast as possible. And they use a technique called adaptive optics, and this is the difference when looking at the moon with and without adaptive optics. So there is a huge gain with that technique, but that technique has huge computational challenge, and this is where, again, as I said, we come into the picture. All ground-based telescopes have the same problem, right? They all are after how to outsmart that turbulence, atmospheric turbulence. The European Extremely Large Telescope, that telescope is supposed to have light in a few years from now, got delayed for various reasons, but it's a gigantic toy for astronomers. Is as big as some of the pyramids in Egypt. And what we've done there to accelerate their real-time processing is mixed precision. We looked at their matrix, we try to compress it. I'm sorry, not compress it. We identify a room in that matrix where we could basically fall back in some of those tiles in the matrix to lower precision. And this gets us a good performance improvement. We looked also at the Subaru telescope. This is a real telescope, right? The other European telescope was mostly simulation. It will be deployed soon. But that telescope here, the Subaru one located in Hawaii, is a real one, okay? So real that they have a GPU cluster located at 14,000 feet. It's probably the highest in altitude GPU system that I know of, okay? It's a bit messy. After all, these guys, they are not system guys, they are astronomers. So one could not really expect a lot. But, we deployed our software into that GPU cluster because we are able to provide them a huge performance gain when it comes to doing the SVD operation. Okay, we released some software a few years ago, and we refreshed our handout. You can go and check it out on ECRC GitHub URL. We are really excited about this project on astronomy. I mean, we're trying to create or build a new chapter from the historical contribution to the field from the region. And, we're looking forward to continue our effort with them. All right. Thank you very much. I don't know. I hope I'm on time.
Thank you very much, Hatem. So sorry, but we can upload you virtually. So thank you very much. So excellent, and you are perfectly on time. So we have a 3 minutes buffer. So so we have a question by Marcin. So is there a risk of introducing non-determinism by using DAG-based runtimes?
Can you repeat again?
Okay.
Oh, I'm getting the okay.
So is there a risk of introducing non-determinism by using DAG-based runtimes?
Yeah, it's a very good question. So, I mean, if you use a dynamic runtime system, there is dynamic there. So dynamic means you don't have reproducibility. And of course, that could be really a problem for, nuclear weapon, type of simulation, where they would really, those domain scientists will require, a digit, reproducibility at the digit level. But there are other way of scheduling those DAGs, and you would use a static scheduler. They may be suboptimal, those static scheduler, and they are deterministic. I mean, in the sense that they will do the same sequence of operation in the same order to make sure you have this reproducibility that you may need. But it may be suboptimal, the static scheduler, because some of the processing you need there may stall while work is available, because they have a dedicated a number of tasks to do, and they won't do any other task, even though some tasks could be available to take and to process, right? So there are pros and cons for between dynamic and static scheduler, and this is how one should look at them. I hope I answered your question, Marcin.
Thank you, Hatem. I have one more question quickly. So thank you. You have showed how you have enabled to have not only more performance, but also what was the nice thing that I like is the integration of KAUST application. So especially in different in climate. So can you share what are the efforts needed? So are you collaborating with the different, and how long it takes to get integration of these packages?
So, I mean, if I look with our astronomers, we started our collaboration back in 2012. And, it took us 6 months to start speaking the same language. I mean, it's not easy. Lots of effort have to be put into the, into the table to, because, they were talking, I mean, a funny story. They were talking for 3 months, for the first 3 months about performance, right? They were talking about performance of, their simulation. And when I heard performance, for me, it was, time to solution, or how many operation, right? I am doing per second, right? This is how I was thinking about performance. After all, this is how we define it in HPC. In astronomy, performance means something else. It means, how accurate the image is. So the performance of their instrument means basically the image at the end, how accurate with this scale ratio metric is. And it took us a few months to to understand that the performance on both sides does not mean the same. Going back to your question, again, that was the story with astronomy, with computational statisticians at KAUST. We were working with Marc Janton, or even computational electromagnetics with Professor Hakan Bakshi. When you have students and postdocs and scientists on both groups that are really willing to get out of their comfort zone, because this is really what it is at the end of the day. You need to get out of your comfort zone and be ready to learn, right? To be ready to learn new stuff that you have never been exposed to. So you need to have a sort of open mind approach, and be ready to be challenged, be ready to ask questions, maybe some question that you have never asked before, but that's okay. I mean, this is the principle, for getting synergies between two groups that work on two different topics. But I'm telling you, the reward really when things start working well between two groups that work on two different aspects of, let's say, an application, or two different domain science. When things start working well, you can really see then the reward, with cool stuff happening that would not have been possible if each of those groups would work on their side by themselves.
Excellent. Thank you, Hatem, again. Excellent, very inspiring talk, and we look forward for other success stories with other KAUST collaborators center. Thank you very much. And now, last but not least, so you will see like a nice talk by Stefano Zampini. So he's a research scientist, an active PETC developer at ECRC, and he will give us like overview about PETC and also discuss about recent advance on GPUs using OpenFOAM and also SSDC. So Stefano.
Okay, can you hear me?
Oh, yes.
Yes, let me share the screen. You see the screen?
Excellent. Yes, perfect. So you can put it full screen.
What is this? Okay.
Thank you.
How can I remove this? Okay. So today I'm talking about, the portable and extensible toolkit for scientific computing. I will give you an overview of the library and discuss some of the success stories that, we are working on at ECRC. And so here is the outline of the talk. I will first, discuss PETC and what are the principles and design choices behind the library. And then I will present a couple of results using PETC. And one is using PETC on GPUs. First, I will describe what are the challenges of using, a library like PETC on GPUs. And then present, very recent results that we just obtained by accelerating, solvers from OpenFOAM using GPUs. And also another work that I'm recently doing is how to do parallel sparse matrix operations on GPUs. And I will conclude with something which is not GPUs but is CPU, and we'll conclude with some of the success stories about using PETC with the SSDC solver, which is a solver that has been developed, is actually developed at the AANS lab of KAUST, led by Matteo Persani. And I will show you some results about how using PETC and why we want to use PETC and what we can get if we use PETC. Okay, so what is PETC? PETC, which stands for, as I said, Portable and Extensible Toolkit for Scientific Computation, is a freely available and supported research code that aim at easy the parallel solution of nonlinear algebraic equations. It is free for everyone, and including industrial users. It has a web page with full of informations and manual pages, and also it has a public development that can be followed at the Git repository. It is supported in the sense that, if you write an email to PETC main, we usually answer, someone from us will answer in 1 or 2 hours tops, and you will get an answer, or you will get someone that will help you throughout your issues with PETC. And it has, the source code has hundreds of tutorial style examples that can be used by new users to learn how to use the library. So the library is written in C, parallelized with the message passing interface, or MPI. So it is distributed memory, but it is callable from C++, from Fortran, from MATLAB, Julia, and also from Python. And the first word of PETC, of the acronym, is portable, and meaning that PETC can be deployed on a tightly coupled system or loosely coupled system, like for example Shaheen or Summit, or it can even run on your iPhone or even Windows if you are a Windows user. So PETC started in the early 90s with the work of Barry Smith and Bill Grob, because they want to have a way of experiment with models, discretization, solvers, and algorithms to solve partial differential equation. And usually the algorithms blurred the boundaries between solvers, discretizations, and models. So we want to have, they wanted to have a central platform to easy the experimentation of the solvers. And why experimenting with solvers is crucial, because with partial differential equation, proving that an algorithm is converging, it doesn't mean that the algorithm that you want to choose is the best one to solve the problem. And I don't know how many of you knows that you can fool GMRES. So GMRES, which is a Krylov method, probably the most robust Krylov method to solve non-symmetric linear systems. you can fool GMRS, and you can design a matrix which is non-symmetric that has a very nice clustering of eigenvalues, but you can design the matrix in a way that GMRS will converge at the worst expectation, which means, you have to have a way to have a different set of solvers that you want to experiment with, because there's no silver bullet. And actually, this is why I put also this quotation here from Barry, and that that says that the role of PETSI is developing parallel is the role that describe the role of PETSI. And what is said is that developing parallel non-trivial PDA solvers that deliver high performance is still difficult and requires months or years of concentrated effort. PETSI is a toolkit that can ease these difficulties and reduce the development time, but it is not a black box PDE solver and nor a silver bullet. That's the main point, because most of the new users of PETSI, they say, oh, now I have this matrix, I just want the parallel solver that will run as fast as possible and solve any kind of linear or non-linear system. But PETSI cannot do this for you unless you put some effort in playing with the solvers. So this is these are the current active developers of PETSI. And 5 of them are in Argonne. One is Barry, Satish, Richard, and the 2 Ongs. And I'm in ECRC. ECRC hosts actually the second largest group of PETSI developers on Earth, and with me and Lisandro. And there are also other developers, from Matt Napoli, for example, is from Buffalo. Jed Brown is from CU Boulder. Toby Isaac is from Georgia Tech, and Mark Adams is from Lawrence Berkeley National Lab. So who uses PETSI? PETSI is used by many different groups that do computational science. By groups in art science, not only in the US, but also in Europe. It is used by multi-physics package from the DOE that has been developed to do nuclear simulations, nuclear reactor simulations. It is also used by other applications of DOE that run subsurface flow and porous media. It's used in CFD. Is used in fusion applications. There is a list, when the slides will be available, all these applications, they have an hyperlink. So if you are interested, you can click on the hyperlink and see what these applications do. Also, PETSI is used by algorithm developers. For example, PETSI has been used to design and deploy, the deflated GMRS, loose GMRS not by the PETSI group, but by researchers, and is also used by researchers doing preconditioning research. So here I'm just mentioning a couple of groups from the domain decomposition community. Also, PETSI is used as a nonlinear algebra solver backend by many discretization packages like Firedrake, Phoenix, LibMesh, DL2, and MFEM. And there are some outer loop solvers like SLAPC, that is for eigensolvers, and Permon, which is for optimization, that leverage on the PETSI capabilities. So what PETSI can handle? So PETSI, this is just to give you an idea of what are the limits that PETSI has reached in the past. This information is quite old, but gives you an idea of what PETSI can do. So, for example, it's been used to solve implicit problem, meaning solving a linear system within a nonlinear application with 500 billion of unknowns, and it's also been able. Also, PETSI has shown to be efficient on 1,500,000 cores on an IBM Blue Gene queue. And the group that ran that specific simulation was from Texas Austin, and they won the Gordon Bell Prize for Mantle convection. This was 2015. So another cool features about PETSI is that it interfaces with many third-party libraries, and all of them, all the third-party libraries that are used by PETSI can be downloaded, configured, built, and installed for you by the PETSI build system itself. And here you have a list of some of the possible packages that you can download and install. And ranging from, BLAS and LAPACK or BLIS, as Bilal was mentioning, even KBLAS or Magma, you can download it and use it from PETSI. You can download Metis, Parmetis, or any other mesh partitioning package that you like, or direct solver packages, and use it from PETSI. So for example, suppose that you want your application is based on FEM, so finite element methods. So you can configure PETSI and say, look, why don't you download and install Triangle and TabGen for me? That these are two packages that do tessellation of the domain, so they produce a mesh for you, a simplicial mesh. So then you may also want to read meshes from generated by different mesh packages, and so you can tell PETSI to download Exodus and MED. That these packages provide API to read meshes. So you can download Pragmatic, for example, and do adaptive mesh refinement. Or you can also download pForest and do adaptive mesh refinement with quadrilateral or hexahedral mesh. You can download, as I said, mesh partitioning packages, because at some point you want to run distributed memory and not only sequential. And you also want to download and install some of the packages that that you can use to dump your solution for post-processing or something like that. So the configuration is very easy, even if you want to use GPUs. So far, PETSI officially supports only NVIDIA GPUs, but there is ongoing work to support AMD GPUs through HIP and Intel discrete GPUs through SQL. And the way you configure PETSI is as simple as passing the path to MVCC compiler and what is the architecture you want to compile your CUDA code for. PETSI also supports another backend, which is Cocos and Cocos kernel, and you can download and install Cocos and use it through PETSI. Also, if you already have Cocos in your system, you just tell PETSI where to look for it. So let's discuss now PETSI. This is a very old picture, but gives you an idea of how the library is structured. And on the bottom of the pyramid, there are the computational and the communication kernels. So in this case, MPI, BLAS, and LAPACK, or KAUST, QBLAS if you want to use NVIDIA GPUs. So these kernels are let's say the first consumer of these kernels are matrices, vectors, and index sets. So the linear algebra part of the library. And on top of the linear algebra part, there are the Krylov method and the preconditioner that make use of the matrices and the vectors to provide the solution of a linear system. And linear solvers are used by nonlinear solvers. So for example, when you do Newton, you want to solve your tangent problem and you want to use a linear solver. So, and if instead your Newton step is embedded in a time-dependent simulation, then it will be an ordinary differential equation integrator that we call the Newton solver for you. So in this slide, you have an idea of what is the workflow of a typical PETSI application. Everything that is in blue is user responsibility, and everything that is in the green box is PETSI responsibility. So for example, if you want to use a nonlinear equation, you have to tell PETSI how your nonlinear equation looks like. And the way you tell PETSI how to compute, given a point in computational space, is how the residual of your nonlinear equation evaluates. And this is the function evaluation here. So if you also want to do Newton, so for example, you need to provide the Jacobian of the nonlinear equation. And you also have thus to provide PETSI a way to compute the Jacobian. So it's the responsibility of the user to compute the Jacobian or to evaluate the function, but then all the rest of the machinery is handled inside PETSI. So Newton's nest which is the nonlinear solver, we'll call the Krylov solver to solve, for example, the tangent linear system. So a little bit of the design behind the library. So every object in the library is an instance of a class, for example, a vector, a matrix, or a Krylov solver. And the main point of the library is that the data structure and the functionality of the specific type of class is provided by specifying a delegated implementation type at runtime. What does it mean? It means that at runtime, I can change the type of the matrix I want to use to, for example, do matrix vector multiplication, or I can change the type of Krylov solver to solve the linear system. So, for example, matsec Aij is a sequential matrix type for using CSR storage, a very standard matrix class in sparse linear algebra. And mat sequential Aij KAUST is very similar to the CPU, but it uses transparently to the user, it uses KAUST, for example, to perform the relevant operations. So the design of the library is based on the operations that you can perform with the objects. So, in other terms, it is designed by the interface and not with the data which is in the object. So, for example, a vector is not a one-dimensional array of numbers, but instead is an object that you can use to add to another vector, to perform a scalar multiplication, so scale the vector, and many other operations. So here is, a typical example of how a PETSI object behaves. So for example, here we are creating a nonlinear solver object, SNES. So every object is associated with the communicator because, we live in the MPI world. So every object is associated with the communicator. So who I speak with. And here in this case, in the second line, I'm setting the type of my nonlinear solvers to be, in this case, nonlinear Gauss-Seidel. Then I issue this call, which is SNES set from option. And SNES set from option basically gives the possibility to the user at runtime to select possibly a different solver or to customize the specific solver. So for example, if at runtime I specify that I want a SNES type of QN, which stands for quasi-Newton, then from this point on, the SNES object will no longer be a nonlinear Gauss-Seidel object, but will be a quasi-Newton solver. So in this case, for example, I'm trying to use an API which is specific to nonlinear Gauss-Seidel, and I'm saying to use three sweeps in the nonlinear solver. And since I change at runtime the type of the solver to be quasi-Newton, this API will do nothing. So which means that I can write a very general code that does not require recompilation if I want to change the configuration of the solver. So, and just to give you an idea of the generality of the approach, this is an example that I like very much, because just by command line, you can play with the linear solvers. Here, for example, we have a Stokes problem, so a saddle point problem, which is very common in the PD community. And you have a momentum block and a pressure block, and you have a coupling here, and you want to solve the linear system. So the first thing that you want to do is, okay, I want to set up a preconditioner, and I want to invert the first block, and I want to use the identity for the second block. How you do this? You just, okay, this is the outer loop. You say, I want to use GMRS. I want to use a preconditioner of type field split, which is the one that I'm discussing, and the type of splitting. And then I'm saying, look, the field 0, which is this one, the field 0 will be solved by an LU. The field 1, will have no preconditioner. And just by command line, I can use this preconditioner in my Krylov solver. So suppose that this precondition, using LU is too much of a requirement in terms of memory, because you know that you can solve your momentum equation in an approximate way. So instead of using instead of using LU, I want to use AMG, and just by changing this parameter, you can now use a GMG for the momentum equation. You can also change the type of splitting and say I want a multiplicative splitting, which means okay, now the application of the preconditioner will make use of this matrix. I can also swap for example, I can swap the fields. I can say okay, now the field split 0 is now made up by what is the field 1 in the original formulation, which is the pressure, for example, and the field split 1 is now made up by the field 0. You can also group many more fields here together. As a consequence, the application of your preconditioner will look like this. So you can also use, for example, the Schur complement. And just by changing the type of the splitting to be of type Schur and diagonal Schur complement, you can now solve your momentum equation always with, for example, with multigrid, and you can solve the pressure equation using, for example, here MinRes without preconditioner. And you can do other things. You can change the factorization type of the Schur complement to be of lower or upper, or you can even use a full Schur complement preconditioner. Okay, now let's discuss, what are current effort and ongoing work of PETSI with GPUs. So in this picture, I think it summarized what is our vision in terms of performance portability in PETSI for the future, because the new DOE machines that are coming in the next years will make use of different hardware like AMD hardware or Intel hardware, and you want performance to be portable across architectures, as Hatem was discussing in the previous talk. So on top of the line here, there is the application. So the application may choose to use CUDA or HEAP as a programming model. You can use Cocos, for example, SQL or Raja. This is completely up to the user, or even use OpenMP or Float, whatever the user wants to use. And what PETSI provides them is the possibility of sharing memory space with the user, so that there are no copies back and forth with what they want to do with their matrix, with the matrix and the vectors that instead are used by PETSI. And as in the backend, PETSI will make use of different and specific implementation for the specific hardware. For example, it already uses QSparse and QBLAS on NVIDIA hardware, and it will soon use RockBLAS and RockSparse on AMD platform. And as I said, PETSI already has a support for Cocos. So all of this is summarized in a paper that we just submitted for publication. And in this link this is an hyperlink. So if you click it, you will get the paper, which is on arXiv. And here is a summary of what we identified in that paper to be challenges in GPU programming for libraries like PETSI. So as I said, the main challenge and what you really want to achieve is performance portability, which means that you want to be able to achieve a reasonable amount of peak performance in various architectures. And this dictates that we have to design specific classes for matrices and vectors that are able to take advantage of the architecture. So we already have an OpenCL backend and a Cocos backend that in principle are already meant to be performance portable, but that we are also planning to write specific classes for HEAP and SQL. So another huge challenge is that whenever you have a CPU and a GPU code, you have to be able to achieve high utilization of both CPU and GPU. And for example, the CPU must keep the GPU busy because any interruption in the GPU queue is detrimental for performances. And we do this with kernel pipelining and kernel fusion within the library. And the main showstopper to really achieve high utilization currently on GPUs is that MPI is, yes, they claim it is GPU aware, but GPU aware MPI means you can just pass pointers that resides on GPU memory to the MPI API. But MPI is not does not really acknowledge GPU streams, for example. So every time you want to perform a communication through MPI, you have to synchronize the device to be so that MPI can really issue the communication. Also, another challenge is that application should be able to decide whether to place the computation either on CPU or GPU, because not all the algorithms map well on GPU and not all the algorithms map well on CPU. Finally, which is actually a challenge that is not really a PETSE concern, but is something that was quite clear from Hatem's talk, is that algorithms to really take advantage of GPU architectures must be redesigned for high throughput, and this requires the thinking of the outer loop. As a PETSE, we can just provide tools for the rethinking of the outer loop, but this has to be done by the new outer loop has to be designed by each specific application. So this is to summarize what we currently offer. I already said that that PETSE has OpenCL and Cocos kernels backend as well as NVIDIA. And PETSE has already a way of sharing the programming model data with users because we use the same approach that is used in SQL. So for example, when you want to access data in a vector, you have read and write accessors so that data movement is minimized. You can bind a GPU metric to CPU when, for example, you have to perform operations that are dominated by smaller latencies, like, for example, solving multi-grid at the cursor levels. And we also already provide specialized assembly routines for assembling matrices on the GPU. And ongoing work, as I said, heap and SQL, and also a proof of concept for using SGEMM to actually being GPU aware even from MPI. Okay, now a couple of success stories. The first one that I want to discuss is OpenFOAM. So OpenFOAM, for those of you that don't know what it is a free and open source CFD software that is really largely used by academia and industry to do complex fluid flows, electromagnetics, solid mechanics, and many other industrial applications. And we recently designed a plugin for OpenFOAM, which is called PETSE for POAM, and is freely available. And if you click here on the link, this is a link, and it will redirect you to the repo. So we recently designed this plugin to expose the PETSE linear solvers functionalities to all OpenFOAM applications. And the idea here is, as Bilal was saying, you don't want to reinvent the wheel. So when you want to solve a linear system from OpenFOAM, you don't want to use probably algorithms that were developed and they were efficient on a specific architecture, but you want to use a different architecture, and you don't want to invest the time to write from scratch a new algorithm, but actually you leverage on PETSE to do this. The idea of the code is that you want to have a single code base. As remember that experimentation is essential when it comes to solve a partial differential equation. And the way we designed the plugin is that it's really very easy to use. And if you're familiar with OpenFOAM, it has a dictionary-based customization. And how does it look like? So here you have, at some point, when you want to use OpenFOAM, you have to write many different dictionaries to customize your application. And one of these dictionaries is related with how you solve your linear systems. So here in this case, I have a linear system that OpenFOAM up is like, for example, if this is a pressure linear system, and I tell OpenFOAM to use PETSI. And here in these brackets, I use all the options, all my favorite PETSI options to solve that specific linear system. In this case, I'm using conjugate gradient, using an AIJ KAUST matrix, which is, as I said, using NVIDIA KAUST, and I'm using an AMG preconditioner, which is GPU aware. For example, I can also have different linear system to solve. Here, for example, the momentum. The momentum, I can use a completely different set of options to solve the momentum. So in this case, I'm using a CPU optimized MKL implementation and using BiCG stub and ILU preconditioner. So in these two options, they don't clash to each other. So as a test case, this is really a toy model, but it's just to give you to show you that the plugin works. I will present very recent results for a lead-driven cavity flow in 3D with 8 million cells and just 20 time steps of ICOFOAM, which is one of the basic applications in OpenFOAM. And in these 20 time steps, I will do 40 pressure solves and 60 segregated momentum equation solves. And I will use algebraic multigrid with Chebyshev accelerated Jacobi smoothing that runs entirely on the GPU. And for the momentum, I will use, this is the standard they use in OpenFOAM, just, using the PETSI linear algebra. And also this run completely on GPU, even though the ILU algorithm doesn't map very well. But we want to have an algorithm that is completely GPU resident. As I said, part of the preconditioner setup is still on CPU. We are in the process of moving completely the setup of the preconditioner to the GPU, but the Krylov solver runs completely on the GPU, modulo MPI. And the results are from using one node of Summit only, because this is a problem that fits in a single GPU. So here on the upper left corner, you have the total time of the application. In red is OpenFOAM and in blue is PETSI. So this is time, so the lower is the better. By using a different number of processes, using one process per GPU. So Summit has 6 GPUs per node. So here, when using 12 processes, 2 MPI processes share the same GPU. And here you see some degradation in performance, and which is known when different processes trying to use the same GPU. So here you have on the right, on the upper right, you have an idea of what specific APIs and assembly for GPUs can do to speed up the assembly of the matrix. And on the bottom row, instead you have a breakdown of the various parts of the construction and application of the solver. So in blue, you have the total time to assemble the matrix. In red, the total time to assemble the preconditioner, and in yellow, the time to solve the Krylov problem, both for the pressure equations and the momentum equation. So you see that doing 40 pressure solves with 6 GPUs takes probably 3 seconds. So second application, which is not an application, but second thing I would like to discuss that we are currently working on with PETSI is how to perform parallel sparse matrix multiplication with GPUs. So this is a standard layout of a parallel sparse matrix, which is distributed by rows in chunks in parallel. So process 0 owns this chunk of rows, process 1 owns this one, and so on and so forth. So what the standard in HPC is to identify the diagonal blocks of the matrix and the off-diagonal blocks of the matrix. So the off-diagonal blocks is usually very sparse, while most of the action is taken on the diagonal block. And to do matrix multiplications, you have to perform some communication first, assemble probably intermediate matrices, and then perform local matrix operation involving specialized API from KAUST. And here are some timings. I just obtained these timings 2 or 3 days ago, so these are very, very new. And this is a sort of weak scaling, strong scaling analysis, all in the same plots. And so if you concentrate here, for example, we are using only one node of Summit with a constant workload. So in this case, the matrix is a million by million, more or less. And this bar is with using six GPUs, and this bar is using 6 CPU. But we can also use many more CPUs on the node, up to 42 CPUs. So here it is strong scaling, and within nodes is weak scaling. So you see that the GPU's operations perform relatively fast, not as 10x or whatever people are used to brand algorithms when it comes to GPUs, but still delivers quite amount of accelerations, even increasing the number of nodes. So in this case, the matrix is 89 million degrees of freedom distributed with 64 nodes and using 6 GPUs here, or 42 cores times 64 cores in total. And this is for various matrix operations. Here on the left is the standard Galerkin product that is used in algebraic multigrid to assemble cursor levels. This is graph squaring. So this is just a symbolic factorization phase only, because when you just want to square the graph to analyze the graph and construct the maximal independent sets that you need to define your smoother aggregation multigrid method. And this is another small operation that multiplying the matrix by the interpolation matrix. And these are the same, but done.
Stefano, we lost you. We can't hear your voice. Hello? Stefano, can you speak?
Can you hear me?
Yes, now, yes.
Okay. No, I don't know what happened. Where is this? Full screen one. Okay. So here is that we cut down further the timings, but just taking the time that takes to do the numeric factorization only, not the symbolic, which means no CUDA, malloc, nothing. So only do the numeric factorization only, plus all the MPI message passing that is needed, and you can see that the speed up of using GPUs is a little bit more. So finally, I conclude with the SSDC solver. So the SSDC solver is a solver that we are developing at TCRC, mostly Lisandro and Matteo and his group, but I also did some work on some of the aspects of the software. And the software is meant to solve compressible Navier-Stokes equations. So these are some of the pretty pictures that we got with the solvers and some of the bullet points of the solver. But I think I have just 5 minutes, so I'll go I will go faster. So the solver is built on 4 classes of PETSI, plus clearly vectors and matrices, but it is built on 4 high-level classes in PETSI. One is TS, which is the ordinary differential equation solver. The other one is the DM, that in this case is a type of plex, which means that we do unstructured meshes. And so DM provides topology and traversal to the application. PETSI-SF is the module of PETSI that does communication for us. And the section is just a very small class that describes the data layout. So Plex is a class that handles any kind of mesh, so simplicial, hexahedral, hybrid meshes. As there has been a lot of effort that has been put in DMPlex in the recent years, but the great thing about Plex is that it really enables dimension-independent programming when you want to traverse the mesh and the various entities of the mesh to construct your discretization, and it also supports non-conforming meshes through pforest. So this is how a mesh in Plex look like. So for example, here we have two cells, cell 0 and cell 1. We have 4 vertices that are 2, 3, 4, and 5, and then we have the edges. And the way it is stored in memory, it is stored as a directed acyclic graph. You know, the arrays are flattened, but the idea is that you have a way of going through these relations. So, for example, I can, given an entity like the cone, like a cell here, cell 0, I can ask Plex what is the cone. So, what are the entity of dimensions -1 that make me up? Which means, the cone of the cell are the edges here, 2, 3, and 4. The same, I can ask what is the support of vertex. So the vertex is supported to the edges 3, 4, and 6. So this way, by meaning of using support and cone and the transitive operations like the closure, we can really do dimension independent programming when it comes to handle meshes. Okay, I will go faster. SF is just a communication layer that abstracts MPI out and uses optimized MPI routines to do the communication for you. And I will go to the results. So the first results I want to discuss are using mesh partitioning algorithms, because we are used to solve very large problems, and we usually read the mesh on a single process, and then we distribute the process. So we design an algorithm which is based on DMPlex, and that is able to distribute the mesh and all the quantities related, like geometry and topology, everything related to the mesh, in different stages, in order to take advantage of the machine topology. Here in this case, in the red curve, I'm using a 2-phase partitioning. In the first phase, I partition to 1 process per node of Shaheen, and in the second phase, I partition within the node. And as you can see, partitioning with many number of processes, I guess is 65,000 processes. It can take a while if you use a standard 1-level partitioning, while using a 2-stage partitioning. This is a logarithm, so this is the gap is huge here. So just in 10 seconds, we can partition the mesh, and the mesh has high quality, like better edge cut and all this stuff. And to close, I close with the scaling results. So as I said, this is an ODE application. So what we care about is the residual application. So in the first set of results here, we have weak scaling. Weak scaling means we increase the number of resources used to simulate an increasingly refined problem with constant computational load per process, which means I fix the number of equations per process, and I increase the number of resources used to solve an increasingly refined problem. And here we have two different, which means that a perfect code will solve this in constant time, and a measure an efficiency measure how well your code is performing. And here we are weak scaling up to 131,000 cores of Shaheen, and this is, I guess, is 500 billion degrees of freedom, and almost in constant time. And this is only because we are using DMPlex and PET-CSF to do the communication for us. So we don't have to write 1 line of MPI. It's PET-C taking care of this. Last application is instead a strong scaling test. This is a realistic application, and this is called the NASA juncture test case, where we simulate an entire airplane, actually half an airplane, because this is a symmetry plane. But here you have an example of the mesh, which is standard in CFD, very refined, close to the plane, and coarser as soon as you go to the boundaries of the domain. So in the strong scaling test, we keep the mesh fixed, we keep the application fixed, and instead we increase the number of resources that we use to simulate the problem. So and here in this case, efficiency is quite good. for example, going from 4,000 to 8,000 processes, the scaling is perfect. Going to 16,000 processes, the scaling is still perfect. Then, 32,000 and 65,000 processes, the scaling degrades, but here we are really using probably 20 or 30 cells per core, which we know it's not optimal from the point of view. So there's a point at which you cannot strong scale anymore, but still, we are very, very happy with the results because, it's very difficult to scale at this stage with a complicated problem, with a complicated solver, and only in an explicit code. And okay, I think I can close here.
Thank you very much, Stefano. Okay, thank you very much. So we can applaud and thank you for this nice presentation. And indeed, like I see, like Alessandro also is a part of the here. So we have like the second group of developer from PETSI here at KAUST. So this is very nice. Also, so do we have question from the audience? So I have a quick question. So we have a lot of developer like at KAUST, and especially like the people from combustion who are using heavily OpenFOAM. So what are I would say your advices how they can benefit with the integration of PETSI? How is it easy? What they should do? So if you have like any, I would say advice, or of course like those who are at KAUST, they should contact you directly, of course. But here, general kind of guidance, if you can.
General guidance, there's not general guide. The point is, as I said, experimentation is essential. So there's no silver bullet. There's no way you can say, look, if you're using solver X with matrix A and architecture C will be as the fastest possible. So and also each application has specific needs. Like for example, you want to have a very robust solver and you cannot afford an iterative solver because you may want to use a direct solver because it's more robust. So there's no single answer for that, and that's why we decided to, let me go back. That's why we decided to base the customization in this way, because this is the user now that is able to experiment directly with what clearly if they have a small application that fit on a workstation size, it's very difficult that they can really take advantage of using PETSI unless probably they have a GPU that they don't know how to use and then they can use. But otherwise, if they have a pure CPU workflow on a workstation size, probably there's no benefit of using PETSI. But as soon as you solve large problems, where you need medium-sized clusters to solve it, then definitely you want to use PETSI or IPRI that is interfaced through PETSI to try to scale your solution phase.
So kind of closing remarks. So I would say like from what you have seen like from these 3 different presentations. So the motto is don't reinvent the wheel. So you have several application libraries that you can benefit from it, and don't think like okay, no, it's very hard. Okay, you have here people who can help you, and you can see like it's like an international effort from everywhere. Here we have also like a comment from Ivan Spiso from Chinica. If you would like to take the mic, feel free. So basically, he said it is usually only if the linear part of your OF simulation, if the big part. Can you?
Yes, I think he's saying something like. Yes, I think he's saying that clearly. If as you were discussing at the beginning, if your linear solution time is something that dominates your application, yes, you want to take advantage of this thing. But if you are instead solving an explicit problem or something that doesn't need this kind of acceleration, there's no point.
So thank you all. Thank you, Hatem. Thank you, Stefano. I really appreciate. And all the attendees, thank you very much. And the slides and the video will be hopefully soon available on the website. So we'll send you the links for that. Okay. Thank you very much. Have a good day. Now it's almost evening for us. And stay safe and see you soon. Okay, bye-bye. Thank you.